So when you see wavelength, a lot of the times you'll see it as second to the negative first as a unit, because a cycle really isn't a unit, you know, it's just like a cycle, it's a number. So generally you see it as second, or you'll see it as hertz. Hertz again is just per second, okay, just 1 over seconds on that. So you'll see it either way. As far as the symbol for frequency, sometimes you'll see it as F, but in the book, and a lot of scientists have moved over to this, you'll see it as nu, the Greek letter nu. It's drawn kind of like a weird V, almost like a curve right there. And it's important to kind of to distinct this because there's a difference between this V and this V, because this would more stand for like velocity, and whereas this V stands for, or this nu stands for frequency. So making sure to make that distinction. It's a little bit hard, especially since it's like, why can't I just write out a V? And that's one of the reasons why. Yeah.
So all waves move at the same speed?
All waves move the same speed. So yeah, all waves of light move the same speed. Obviously,
Sound.
waves of light will. Obviously, a sound wave could be different than an actual like water wave. Like a water wave is not moving at the speed of light, right? I'd be terrified if a water wave was moving at the speed of light.
Surfing on waves that fast?
Nope. I don't think there's a physical wave of water that would be moving that fast. But light itself, all light travels at the same speed regardless of what type of light it is. It's just that for frequency, it's traveling at the same speed, it's just that this cycle happens more often the higher the frequency goes. So it's like the difference between this wave and that wave. Where like it's still traveling the same speed, it just goes up and down, up and down, up and down, up and down more times than it would with this wave. Does that make sense? Yeah, I know it's a little bit of a weird concept to think about, but yeah.
Does anybody know how much faster light is, or the relationship between light and sound?
Yeah, I don't
Light sounds slower.
Light travels 186,000 miles per second.
That's like
7.5 times around the surface of the earth in a second. Sound takes 5 seconds to go 1 mile.
So it's like
Okay?
almost a million.
So in a thunderstorm,
Yeah.
when you see the lightning you're seeing instantaneously, because if it's a mile or two away, 186,000 miles a second, basically the lightning occurs, you see it. But the sound takes 5 seconds to go a mile, so you can tell how far away the lightning is by counting, and every 5 seconds it was a mile away. So 10 seconds is 2 miles away. Okay, so there's just a big difference on that. And so that's just kind of an interesting application. Anybody run track? Yep, you run, okay. Sometimes if you run in like a 220 or something, the starter's at the finish line. You're supposed to go on the smoke. You're not supposed to go on the sound because you can see the smoke before you can hear the sound. The difference in the speeds of the waves. Just little tidbits there for you.
So now we're going to our actual formulas that can help us describe our properties of the wave here. So, on the back here. I'll erase this. Okay, and let me move this down here. Hot. So, like we mentioned, since all you marked waves travel at the same speed, the longer the wavelength, the lower the frequency we just talked about. So, if we're going to describe this as a formula, if we're talking about the wavelength and the frequency, what do we think we're going to put here as the formula? If we know it travels at the same speed, and we have an inverse relationship, what do you think goes here?
1 over.
Not 1 over. So the speed is always the same, right? So if we had something and we increased it here, there's two variables here. So if we had something and increased it here, what happens to this variable? It has to decrease, right? Because at the end of the day, c is always going to be c.
Yeah.
So what do you think these two variables inside are going to be?
Wavelength and frequency.
Wavelength and frequency. So we're going to represent that as our wavelength, our lambda, and then our frequency, which is our nu here. You'll also see this sometimes as C equals lambda F, like I was saying earlier. Frequency could be either F or lambda here, but most scientists tend to use lambda.
Wait, so what is that below the up arrow? Is that a U?
That's lambda, that's new, that's what I was talking about. So new is, it's kind of like a V and a U almost combined. It's got a little bit of a curve here and a straight line down there, and that's how you're going to use new here. So this is what we're dealing with, not this, because this is just velocity, right? Our V here, if we're just using lowercase v as velocity. When we use new, we're referring to our frequency, and so it's really important to make sure to distinguish that, because there are some cases where you would need both a formula, and so it can be very confusing if you don't have those written down correctly. So make sure to make that distinction with those. Alright, so like I said, they're inversely proportional, right? So how do we describe inversely proportional?
If one goes up, the other has to go down.
One goes up, the other has to go down. And we can use that as a definition. What I use is just like as one gets better, as one gets bigger. Again, talking about our frequency and our wavelength, right? So the next thing we need to know here is how energy relates to these. So the energy of the wave. So it's kind of spoiled already here, but I didn't even cross this out here. So the formula here we're going to use is energy is equal to Planck's constant times frequency. So what does that mean between the relationship between energy and frequency? Is it directly proportional or inversely proportional? If I raise the frequency of a wave, will the energy increase or decrease?
Increase.
Heard increase. Everybody in on that? Yeah, it will increase, right? Because we got it on different sides of the formula. So those are two really important concepts. Is that energy, as energy goes up, our frequency goes up. As our wavelength goes up, it gets longer. I proved lambda twice. as our wavelength goes up, our frequency goes down. And again, we can use these equations here to describe that. So we have our speed of light is equal to our wavelength times our frequency, and we have our energy is equal to Planck's constant times our frequency. Planck's constant, again, just a number to kind of to give the right scaling to the unit that we're talking about, and also there to make sure that the units work out. Yeah. So to do this, I actually want to go through just like a quick practice problem for both of these, just so that we can get comfortable with using these equations here, because you'll see these a lot. So let me pull them up. I didn't have a chance to print them out, unfortunately, but I do have some questions here. So let's start with.
Can you just email it to me super fast? And then I can
Yeah.
at least sign it.
Yeah, I didn't have a thing for this one because I just found it online. So I was trying to find a good question here, but here's it might just be better if I write it out.
Okay.
This one, yeah, because I basically found two resources online. They have a bunch of other questions, but I just want them to curate with one so that we can move them towards top spectrum and whatnot. So here is our first problem that we're going to work with. So let me go ahead and just freeze this here. We're going to erase this board here.
While he's doing that, y'all in math, what's the math XY equation for direct proportion?
1 to 1?
No, how would the equation look if you were a direct proportion with X and Y?
Just the
X
side
equals
is
Y.
Equals Y.
X equals.
Usually it's Y equals MX or KX, right? Like you can do that.
Yeah.
Y equals MX plus B, but B, the y-intercept 0. Okay? So M is the slope, or you can use K, there's always a constant. For inverse proportion, it's x over y. No, it's gonna be x times y, k equals x times y, right?
Sure.
That's what you learn in math, and you learn it in math about that, and you have learned about inverse and direct proportions and the equations in math. You do that so you can apply it to a real subject, something that's real, rather than just x and y. But that's why we have to have h. H is the same as the slope in y equals mx. H is that constant that changes the proportion to an equality.
Alright,
Okay, go ahead.
so here's our first one. Wavelength of orange light is 620 nanometers. So what's our frequency? That's what we're trying to find. So first, what equation do you think we need for this one?
The speed of light.
So speed of light equation. So you're saying that c equal to what?
3.30 times.
Okay, so that's what it's equal to. Alright. But what is c equal to in context of this question?
Wavelength and frequency.
What was that?
Wavelength and frequency.
What were you saying?
Wavelength and frequency.
Okay, cool. I think that's what you said, and I couldn't tell what you were saying, so I just wanted to get a second opinion on that. So, wavelength and frequency. So, how do we start to solve this? What do you think?
3.00 times 10 to the 8 equals 620 or so, whatever that number.
Okay.
620.
I didn't draw this as new. I'm getting lazy too. There you go. That's a bad
620.
idea. One more time. There you go. And you said the 620 nanometers, right? And then on B. See, even sometimes I see it, I'm just like, I get unfocused. I'm like, it's a V, but I gotta remember. And this is something that you might do a lot too. Remember, it's new. We're talking about new here. We're not talking about velocity. We're talking about frequency. So we have this set up here. What's our units on light again? Meters per second. All right. I kind of cut you all off. I feel bad for that, but it is a whole nother way here. So what do we need to do with the next? Oops, I dropped that.
Divide
Divide by 620.
So I heard divide by 620. Any other thoughts?
3.3 times 10 to the 8 nanometers.
So yeah, so convert this to nanometers per second, is what you're saying? So we could do that. I think an easier way to go about this problem is just convert the nanometers to meters, right? Because, we're dealing with this whole seconds thing here too. Theoretically, you can do it either way, so either way is correct. But I personally like to do it this way, but do y'all want to do it by converting this to nanometers? Because it depends on what y'all want to do on this one. So I saw a few no's, I saw a few yes. What are we thinking? Converting this to nanometers or converting this to meters?
Converting that to meters.
Or meters. Okay. So we'll convert this to meters. So how do we do that? What is this going to be in meters?
Who remembers how many nanometers on a meter?
I don't know, is it like 10 or not?
Not 10.
Is it like
Negative
negative 9?
10 to negative 9. I heard that. You said 9 as well. 6.
6 is
not 6.
Micro.
Yeah, micro is 6. Yeah. So nano is going to be what?
Negative 9.
Yeah, 10 to negative 9 meters.
That's the 6.
So, what is this going to be in meters? If we're going to bring this up to meters.
0.6
It's gonna be 6 zeros instead of negative 7.
I heard, okay, so I heard it 6.20 times 10 to negative 7. Any other thoughts on that one?
Yes. That is correct.
Okay, that's correct. We're agreeing on that? Okay, yeah. So, 6.20 times 10 to the negative 7 meters.
How did you get that? What did you do to get that?
You moved the decimal point to place the numbers, so it's 10 to the negative 9, now it's to the negative 7. You moved the decimal point to place it.
I understand. Yeah. So you moved, so it's normally it would be 10 to the negative 9. if you just multiply it that way, but then moving the decimal place 2 over to make it in proper scientific notation becomes 10 to the negative 7. Is that what you were trying to say? Okay.
I just wanna make sure everybody knows how to do that mathematically.
Yeah. Alright. So we have this, M, and meters, and we have our new, we have our speed of light, 3.00 times 10 to the 8 meters per second. And then now, what do we need to do?
Divide by 620.
Divide both sides by 6.20, right? Times 10 to the negative 7 meters. So, go ahead and do the math, and let me know what you get for the frequency here.
Shoot.
Yeah, make sure when you're doing scientific notation, parentheses. Parentheses are so super important to make sure you actually have what you're trying to calculate here.
Uh, 4.84 times 10 to the 14th.
4.84 times 10 to the 14th.
Yes.
Alright. So it's 4.84 times 10 to the 14th. Everybody getting similar answers or different answers? Yeah, make sure everybody gets it first. I want to see if we have any other answers.
What'd you say? 4.84 times 10 to the 14th.
Yeah, 4.84. Okay. Everybody else getting around that number? Yeah? Okay. Yeah, that's exactly right. So it is 4.84 times 10 to the 14th. What's the units on this one? Seconds. Square?
No,
Seconds.
seconds, that.
Seconds
the
negative to the
thing.
negative
Seconds to the negative what?
first.
Yeah, second to the negative first. I couldn't hear first or something, but yeah. Second to the negative first, and a couple other people are saying that as well. Right, because what do? We have this meters per second, we divide it by meters, the meters cancel out, we're left with something over 1 over seconds, right? Does that make sense?
Oh, yeah.
Yeah, like you got meters per second, you divide this by meters. So if we were doing like our dimensional analysis thing, we would set it up like this. We're dividing by meters, and so what we're left with is 1 over seconds. Right? Make sense? Cool. Alright. So yeah, if we're going to do this in... I don't really want to do this. Well, no, we can do this in sig figs. What would be our sig figs here? So what's, out of all these numbers, which one,
2,
2, right? Where do you get 2 from?
the 620 nanometers.
620 nanometers, right? So, minimum sig figs is 2, so this would be 4 point what?
8.
Yeah, 4 point. That's it. Make sense? Cool. So that's a problem with, that you'll see when you're relating those. So I got one more problem we can cover here. And I'll let y'all, instead of walking you through it, let y'all go through and try to solve this on your own, and then we'll reconvene and figure out what it is. So, let me go ahead and pull it up and run over here. So we'll talk about what a photon is eventually, but this is essentially the problem is, so this is something you'll remember in the future, but a photon has a frequency of, the number is 2.68. 6 hertz. What's the symbol of these hertz? So, photon has a frequency of 2.68 times 10 to the 6 hertz. What's its energy? So, another important information you need to know is Planck's constant. be pretty important. Let me see, is it in your notes or is it?
6.626 times 10 to the minus 34.
Gotcha, thank you. So H,
626.
yeah, I got 66.
No, 6.626.
Oh, gotcha.
That's okay,
Is that
I got a mountain rule of good part.
You said 10 to the negative 34th, right?
Negative 34.
Yeah. Remember that part.
And it's joules
Yep.
times seconds.
So that's what H is. So,
That will always be given.
yep. Why does this worksheet that I found doesn't give it? That's weird. Oh no, it does. It's just not on the first problem. Weird. Weird.
The negative 34.
Yeah, that's negative 6.66 times 10 to the negative 34 joules per second. Yeah. I got you.
No, I got my
Oh, you get your answer? Oh, okay. Let me make sure I remember the answer before.
answer. Is that number always the same?
Yeah, that's why it's a constant. It's there as a scale to relate the energy and the frequency. This is not necessarily a one-to-one scale of frequency and energy, so they use this one to put the scale in perspective, and two to make sure the units line up.
Anytime there's something proportional, when we say directly or inversely proportional, you have to have a proportionality constant to change it from a proportion to an equality, to make it equal. That's just a math principle.
Is this right?
I think so, yeah. Yeah, that is.
And then,
I don't think we'll get to photoelectric since I wanted to go through these equations, but I did write aloud.
No, but yeah, it's very important that they do a lot of practice when
Yeah.
writing your punch sheet.
I actually do have a sheet, but I want to save that for when we get to what's the space in that way. Because what it does is you have practice with problems and then you derive that equation from your two equations. So it's really interesting. I think that'll help out a lot. And then, as one of the review chapters, we'll then pull a bunch of equations. All right. Let's see where we're at. So yeah, remember with hertz, what is a hertz?
yes.
Seconds to the negative first.
Seconds what?
To the negative first.
Yeah, seconds to the negative first. One hertz is 1 second to the negative first. You'll see it as both when we're talking about frequency. It's just that this is named after the guy that figured a lot of stuff about it. So seconds times seconds. So, seconds times seconds negative first. What do you think? So if you have a seconds, and then you're times by 1 over seconds, what do you get?
Zero.
Not 0.
One.
1?
Seconds over seconds.
Seconds over seconds equals what? Right? So it's all just canceling out units like we just did in divisional. So yep. That's it. That's why keeping track of your units and learning how to cancel these units out are super important.
Wait, what?
Huh? We're just confused on what I said.
Oh, yeah, I didn't know you.
Oh, I was just saying that's why being able to cancel units out and making sure we keep track of our units are super important. It's all that stuff, especially in chemistry.
You guys can always have fun. When's your birthday?
Today.
Oh, is it actually?
And yesterday and tomorrow.
Oh, I see.
No, it really is.
Alright. Everybody think they got a decent answer?
Yes.
No? Everybody at least attempted the problem. Alright, perfect. We'll start from there. Okay, so what formula did we use in order to solve this?
E equals HV.
Energy equals HV, E equals HV, yeah. Right? Oh, well, sorry, H what? What is this? This is not V, it's what?
Lambda.
This is not lambda.
New.
New, there you go, yeah. Lambda's wavelength, this is new. It's important to make sure you have that distinction. It's not a V, it's a nu. Because again, if we're talking about V, a lot of the times in science, with V, we're talking about velocity. So it's important to make that distinction.
But you said it's not me, it's new.
Yeah. It's not, yeah, me, science, kind of something.
It's not, instead of saying B.
Yeah, it's not like V, it's me, yeah. Close enough. Anyways. So, what do we do from here? What do we start with?
Put in like stuff you know.
Put in the stuff you know, okay. So you skipping ahead to the next part, but yeah, you're exactly right there. So put in the stuff we know. What is H?
2.68 times 10 to
It's 6.626 times 10 to the negative 34.
There you go, yeah. Hey, well, it means it's just everybody's on the same page, right? It's a little creepy, but we're all on the same page here. Okay, what about new? What is new?
2.68 times 10 to the 6.
So this number right here. Does that make sense?
Yeah.
Everybody? All right. Is there any units we need to convert in this one?
Well, I don't know how to do it, but
I
I don't know if
you didn't convert?
Yeah.
I mean, like what's a hertz?
1 over second.
1 over second. So really no, but just to keep in context with the joules, you're not going to have, like joules per second over hertz is going to just be joules, right? Because it's 1 over second. So it's important just to make it, when you're in problems like these, to convert it to 1 over seconds if you haven't already, but it's a 1-to-1 ratio because it's the same thing. Just so that you can make sure you have the right units for what you're trying to find. So I would convert this to just 1 over second. Which that's not really a conversion, right? Because we know that 1 hertz is 1 second to the negative first. So, what do we do now?
plug it in your calculator.
Multiply them together, and then what do we get when we multiply them together?
Move it away.
Give me some answers. I heard briefly 1.7 something.
1.78 times 10 to the negative 27.
1.78 times 10 to the negative 22nd. Any other answers that y'all got? No? No? Everybody got that? Perfect. Then everybody is right. 1.78 times 10 to the negative 22nd, or 27. What's our units here?
Joules.
Joules. Boom. Good job. Alright.
That's like a tiny number.
Yeah, it is pretty tiny. I mean, again, this is talking about a single photon, which we'll learn about what a photon is eventually, but when we get into it. But they're not very big. So just one in and of itself is just that. But when you have situations to come up with photons, it's usually never just one. You know? Like it's not just one. You'll see what I mean when we get there. That's why it's a little weird that we're talking about photons now. We'll describe photons a bit later. So, speaking of, we'll do one more problem here. So, it is just similar. It's going to be combining the two concepts here. Just to do another problem to get used to these calculations here. Because I also want to not necessarily start the lab today, but we have an online lab that we can do. It would be better to be able to just knock out the whole lab on Thursday when we have more time. The lab itself might not necessarily take too horribly long. So, calculate the energy and wavelength of a photon of light with frequency of the number that I'm going to put. So, calculate energy I forgot to note this, but for those of you at home that are watching this, try to make sure to pause the video at each question. You already have some time to work on it initially, just to pause, but if you need to work on it on your own time, I definitely suggest taking a break to make sure to see if you can calculate this on your own. Alright, so let me write down the rest of this problem. I can't spell. Anybody else do that where they put the in the wrong place?
Yeah, I can't
It's
spell
TA.
link.
No, it's TH. I know it's TH, and I literally corrected myself. I do that all the time, I swear. Calculate energy and wavelength. Then that doesn't look like an O. What's the frequency we're dealing with? 6.1. To the 14th. There you go. So two things we're looking for. We're looking for wavelength and we're looking for E. Again, H being equal to 6.626 times 10 to the negative 34th joules per second. Speed of light, y'all should remember speed of light. What is speed of light real quick?
3.00 times 10 to the 8
What's the units?
meters a second.
Meters per second, yeah. That's one that you will have to know. I don't think most places will give you speed of light. I don't think we will be giving you speed of light, but it's not too hard to memorize that. It's just 3.00 times 10 to the 8 meters per second. Alright, so go ahead and try this problem on your own. Maybe I'll find work on that. I'm gonna get some water too. Yeah. Yeah.
I think I know how to find the energy equation, but it's beautiful. I mean, wavelength is.
Wavelength? Okay, so you have two formulas, right? And so basically what you're trying to do is figure out how does your frequency,
Oh, wait.
you got it? No clue? So you have the first equation, which is energy, right? And you can find energy using the wavelength, right? Or sorry, not using the wavelength, using the frequency, right? So is there a way from one of these equations that includes wavelength and frequency that you can maybe solve for not? Yeah, first one, right? Because you've got speed of light is equal to your wavelength times your frequency, right? So basically you just need to manipulate that equation to find your wavelength. Like we were doing the first one. Yeah. So it's just a two-step problem using two separate equations. Yeah, what you got?
No way.
So this
Yep.
is the equation for the wavelength, right?
So, yeah, it relates wavelength and frequency together, right?
Yeah, that's wavelength.
Yeah, there's a wavelength.
Okay. So that's H and V.
Uh.
That's lambda and nu.
Well, it's H and nu. This is H nu.
Okay, so
Yeah.
that's not.
Yeah, that's new. Yeah, it's not V, it's new. Yeah. Especially right now, we're just talking about new.
Okay.
There will be an equation, I think, if we're going to be talking about it, that covers V and nu in the same equation, so it's important to make that distinction now. because V is more of this related to velocity, which is essentially the speed of something. So the units for speed is the same as the speed, or the same as velocity. So that's why you want to make sure you keep those in track.
So for that, the new frequency, right? So on this, we don't know the.
We're trying to find the energy, and we're trying to find the
Okay,
wave.
gotcha. Figured it out.
You got it?
Thank you.
All right, no problem. Quarter till.
I keep thinking second period, you thought they would tell them to stop and then
So we'll get to like 141 and we'll just talk about what we got for both of them and then that should be it for today.
Well,
And then tomorrow we'll just talk about atomic spectra and our different wavelengths for the different electromagnetic radiation that exists, as well as a lab with the photoelectric effect, which we'll learn about in the lab. And also, we'll probably have more time since it's a longer period, so I'll probably go to the next activity. Okay, so we'll go through this real quickly just so we can finish it out before the bell rings. So what do we get for our energy?
4.085 times 10 to the negative 19.
4.085 times 10 to the negative 19. Any other answers for that?
I
No?
got 1.075.
Ooh.
Yeah, I got completely, wait, for the what?
Energy.
just show how to calculate.
Yeah, let's start with calculating. Okay, so energy, what's our equation for energy?
Yes.
H
New.
New, yeah, there we go. Now we're starting to get it. Alright, so what are we putting on H? What is H?
6.6.
Oh, wait.
2%. What is new? Oh,
That's
okay,
divided by
frequency.
one.
6.165.
That makes more sense.
Good job.
Play.
Hertz, which is what?
1/6.
Yeah, 1/6. So yeah, what did you end up doing, Clay? Is it just?
I just hit them all instead of multiplying it by.
Oh yeah, that's probably what ended up happening with a lot of people. So yeah, that's how you calculated that. And yeah, we're right. We got 4.1 times 10 to the negative 19.
Boy, if there's a way to screw it up, I can do it.
It happens. That just comes with more practice. The more you practice, the more you're comfortable putting
I
it
like
in.
that back in the searches.
What about with frequency? So let's set this up. C equals lambda nu, right? That's what we use.
Yes.
All right. So C is what?
3.00 times 10 to the 8th meters per
Meters per second. All right. And then we have lambda. We don't know what lambda is, right? And then we have nu, which is again what?
6.165
Yep.
times 10 to the 14.
165 times 10 to the 14
Hertz.
hertz.
Oh, that's what I got.
Which again is 1 per second. So what do we need to do in order to find lambda?
Right.
Divide, right? Right here, this marker's running out. But then we get lambda is equal to, what do we get?
4.87 times 10 to the negative 7.
4.87 times 10 to the negative 7. What's the units?
Meters.
Meters.
That sounds about
Anybody else have any different ones? Different answers on that one? No? Good. Yeah, so that's exactly right. 4.87 times 10 to the negative 7 meters.
I like that you don't have to convert the units.
What'd you say?
I said I like the problem where you don't have to convert the units, because that's so weird.
You like the ones that you don't have to convert units? Yeah. Yeah, and this one we didn't have to convert because we weren't finding, this was in the nanometers, right? We were just using frequency like here. But remember, if you do have, if you're given wavelength here and you're given it in nanometers, you gotta make sure to keep all your units to where they will cancel out if you need them to cancel out, for example. Like we did on the first one, where we had to convert nanometers to meters.
that problem too fast.
It happens, and I get it, but it's, like I said, the more you do it, the more you're comfortable with it, so. And we'll be trying to get as much practice in as we can, just doing the problems and doing the math on it, so. Yeah.
Hey, you know, oh, hey, you know that in Crucible, Abby is, yes.
I can't give them to you, because everybody wants to.
Are you talking about the Mountain Dew